So in the circuits that we've been discussing so far, you might be wondering kind of what's the point of the circuit? You have a battery connected across two resistors, but they're really not doing anything. So I'm going to go through kind of a practical example of where resistors are used and why we use them. In the video that you watched, it explained what an LED is at a very basic level, light-emitting diode. And one of the important things probably the most dramatic moment is when he's burning up the LED and all the smoke comes out. So that's obviously not something you want to have happen. So let's go through an example circuit with an LED. I'll draw the schematic first and then we'll wire it up on the breadboard so you can see how this works to get an idea of how we actually use resistors for practical circuits. So we'll start with a 9-volt source, which is common for battery applications if you're running it off of a 9-volt battery. And in this example, we're going to use a red LED and connect it through a switch. We'll talk a lot about switches later on, but let me draw the symbol for the LED first of all. And again, if these symbols kind of don't make a lot of sense and you're thinking, how do they even relate to the circuit, I'll try to go through that to help you understand the connection between a schematic, which I'm drawing now, and an actual circuit that you would put on the breadboard. So the schematic symbol for an LED kind of looks like an arrow, but the difference being that there's this kind of like little kind of line that comes out of it showing that it puts out light. The LED, as you remember from the video, has a positive and negative lead. The anode is positive. The negative side is cathode. And it's important to keep track of that when you're wiring up circuits, because if it's wired backwards, you can easily damage the LED. And so that's the symbol for the LED. And we're going to connect it then. If it was connected to the rest of the circuit, it might look like this, connected to the battery. And then I'm going to put a switch in here that we can use to turn this circuit on and off. And I'm just going to show a very simple switch. And a switch is basically a device that has some mechanical contacts that allow current to either flow through the circuit or not flow through the circuit in this case. So I'm going to connect that switch to the LED like that, and that's our complete circuit. So it's kind of obvious looking at the switch that if that switch is open or not pressed, and push buttons kind of might physically look like this, you've got two wires coming out, and you have a little push button on the top. Those are what you're going to be using later on in your circuits when you're breadboarding. So internally, they have a mechanical connection that if you press on the switch, it makes an electrical connection, allows current to flow through there. The problem with the circuit as we have it drawn here, though, is that there's no resistor in the circuit. And if you remember from the video, the voltage, the forward voltage, which is called VF on an LED, for a red LED is about 1.7 volts. I think he says it's 2 volts. It's closer to 1.7 volts. And the problem here is that the battery can supply 9 volts, but the forward maximum voltage that the LED is going to drop is 1.7 volts. And so if we push that switch in this circuit, the voltage from the battery, it has a lot more current. It'll try to force more current through that LED to bring the voltage up to 9 volts. And unfortunately, in this case, the battery would win, and it would destroy the LED. So I'm going to modify the circuit a little bit to add the resistor to it. So now we've added the resistor to the circuit, and one of the questions that comes up, well, what's the value of that resistor? And we have to look at this whole circuit to calculate this. I'll call it R1 here. That's our one resistor that we have in the circuit. So there's one other important piece of information we need to know before we finish that circuit, and that's how much current is flowing through the LED. So a typical LED current, and I'm going to call that I LED. It can also be called IF, the forward current, is typically about 10 milliamps, 0.01 amp, or 10 milliamps. And they can usually go up to something higher, probably on the order of 20 or even 30 milliamps. But that's a typical amount of current that will light up the LED. If we don't have that information, we can't really complete the circuit. So the first thing we have to look at is on this resistor, we need to figure out what the value of the resistor is. But like with Ohm's law, anytime we have to calculate a value like this, we need to know two parts of the equation. So in this case, we need to know the voltage of the resistor, and we need to know the current flowing through the resistor. Now, because this is a series circuit and all of the components have the same amount of current flowing through them, the current's going to be the same as the current that we're designing the LED to light up at. So that's going to equal 10 milliamps. The voltage across the resistor, well, we wouldn't know that without looking at some values here. But we know, for example, that the LED is 1.7 volts across it. That's our forward voltage. And we have 9 volts here, which means that the rest of the voltage has to be dropped across this resistor. And I'll draw the plus and minus here. So how do we calculate that? Well, in the circuit, we have our voltage source is going to equal the voltage of the resistor plus our forward voltage of the LED. So, whoops, sorry, that got a little low there. So we're going to say 10 volts, whoops, let's make that 9 volts. Our source voltage equals 9 volts, and that's going to equal the voltage across the resistor, which we don't know, that's what we're solving for, plus VF, which we know is 1.7 volts. So I'm just going to fill that value in here, 1.7 volts. So we can solve for VR by subtracting 9 minus 1.7. So our voltage across the resistor ends up being 7.3 volts. So we've got two parts to the equation now. We know the current through the resistor, I sub R, and we know our voltage across the resistor. And now we can use Ohm's law to calculate the value for that resistor. Okay, I wanted to take a minute to clarify a few things as I was reviewing this. First of all, this 10 milliamps that I just kind of pulled out of my hat, that's a design value. And that's based on, if you looked at the data sheet for an LED, it would specify a current, maximum current, or a typical current rating. And that's 10 milliamps is a pretty typical value for these small LEDs. Also, I rewrote this equation for V sub R in a little bit better way, where we take VR equals the source voltage minus the forward voltage drop of the LED, and that equals 7.3 volts. So, the current flowing through the resistor is the same as the forward current of the LED. So I'm going to use Ohm's law here, R equals V over I, to calculate the resistance value. We also have to focus on the actual value of the components near the resistor itself. So we could call this actually R equals V sub R over I sub R if we want to be a little bit more specific. So in this case, the voltage across the resistor we calculated as 7.3 volts divided by I sub R is 10 milliamps, 0.01 amp. And if we calculate that out, that ends up being 730 ohms. Now, you'll find that it's pretty hard to find a resistor value of exactly 730 ohms. That's not a typical value. And when we talked a little bit about resistors, they're basically in what's called a cardinal ordering system, where they have specific values that are typical that you find. And so probably the closest typical value you would find is 750 ohms. And I believe that's a value that's in your resistor set that you could use. So that would be the value of your resistor up here, 750 ohms. Okay, so I've collected most of the parts I need here for this circuit. In the breadboard video you watched, you'll remember that these supply lines here are called the bus lines, I think. Sometimes there's a gap between them, and you can usually add a little wire to connect them if you don't see the colors connecting. But that's very important. In this case, this breadboard, the lines connect all the way across. So the reason I'm bringing that up is that I've got my power supply connected. It's a little bit big to try to fit on the screen. What I'm going to do is plug in a red wire here for the positive. Actually, let me put it on the top. It doesn't really matter. But I'm going to put it on the top and connect that to the power supply. We'll take a look at the circuit closer up in a little bit, but I want to keep the schematic on there too. And then I'm going to take a dark wire, usually black is the color that represents negative or ground, and I'm going to connect it on the bottom. And traditionally, a lot of electric circuits, they don't have to be connected this way, but it's very common to wire them so that the positive terminal is near the top and the negative terminal is near the bottom. So that's the way I've got the power supply connected, red on the top, black on the bottom. Okay. Next, what I'm going to do is I'm going to wire in this switch. Now, you might think, well, that doesn't have anything to do with the connection on the circuitry here. Well, the point is that a lot of the times with circuits, there are lots of different points that need to be connected to the positive and the negative. And so if we've got those connected, that powers all these strips with the supply voltage, and we can get to them easily in the circuit. Next thing I'm going to do is plug in the switch. And if we take a look at our schematic, it's connected to the 9-volt positive supply. And I'm going to just run a wire from the positive to the left side of the switch, like that. You have to make sure you're keeping track of which row they're connected to. And then the other side is going to connect to the resistor up here. So I'm kind of looking at the schematic as I go. Now, in my case, I didn't happen to have a 750 ohm. I've got an 820 ohm. Let me orient that the right way there. So my current reading will be a little bit different. So now I've got the resistor connected there. And the LED, again, the positive side is the longer lead. In this case, it's already bent. And I'm going to go all the way from there to ground, like that. So what we're looking at here, even though it looks physically very different, obviously, than the schematic, we've got our supply voltage here, which is the 9 volts positive, going to the switch, and it's connected from that bus line to the switch. The other side of the switch is connected to the resistor. The other side of the resistor is connected to the LED, and the LED goes back to ground. So, if everything's wired properly, I should be able to push the button, and the light should go on. Okay, so this is a little bit of a closer view of the circuit now, and you can kind of follow this path. The current would flow through there, through this wire to the switch, through the resistor to the LED, and back to ground. Now, I could have clipped the leads directly to that line on the switch or the ground there, but again, I like to use these buses. It makes it a little bit easier. So when I press the button, as you might expect, the light comes on. If the LED doesn't come on, it could be that it's miswired. Like, for example, the first time I connected this, the switch was actually in the wrong rows like this. They have to be connected because remember, on the breadboard, each one of these columns, all of those are vertically connected to those lines. So the switch has to go between those 2 points there and there. So when I connect that, press it, LED comes on. Now I'm going to measure the voltage in the next step, and we'll measure the voltage across the resistor, across the LED, and also measure the current. Okay, so at this point, so now I've connected these clip leads across the resistor, and we're measuring voltage here, 20 volts. And if I press the button, let's see what voltage we end up reading. We end up reading approximately 7.03 volts. So I'm going to write that in here. Now again, that voltage rating, trying to get down to that millivolt range is pretty precise for what we're trying to do. But we'll see what we end up with on the LED. So I'm going to move these probes over here, the clip leads now over to the LED, and measure the voltage. Press this again, and we end up with 1.89 volts. Okay, so if we look at Kirchhoff's voltage law, which basically says that the sum of the source voltage minus the voltage drop should equal 0, we end up with, if we subtract the 9 volts minus the voltage across the resistor minus the LED, we come up with 0.08 volts or 80 millivolts. And that might be due to a number of things. The readings might be off a little bit. The voltage source might be off a little bit. But we're well within 1% for sure. And so that's a reasonable value that we'd expect to see. So next, let's check the current. We had kind of went for a target of 10 milliamps. Now, because my voltage across the LED is, the VF is a little bit higher and the different resistor value is a little bit different, we probably expect that there's going to be some error here. A couple of things, again, very important with measuring current. We're going to set this to 20 milliamps down here. And whenever we measure current, we have to break the circuit. So what I've done here is I've disconnected the resistor. I've unplugged it because the meter has to become part of the circuit. I'm going to connect that positive on the resistor. That goes around to the meter on this side. The negative comes back around and loops up to the LED. Now, if you don't do this, if you accidentally measure across a voltage source with the current reading set this way, you'll blow the fuse inside. And I've done that. It happens. You just try to be as careful as you can when you do it. And that's why I gave you a spare fuse, and I'll probably have to show you a quick video on replacing that fuse at some point. Okay, so now we've broken the circuit there. And I'll zoom in on that a little bit so you can see how that works. It's a series circuit, so you can really break the circuit anywhere. But again, the meter is going to become part of the circuit. And if I press the button now, we're measuring 8.45 milliamps flowing through the circuit. So let's see if that adds up with the math. Okay, so when we do that calculation, now what we're trying to find here is the current flowing through the resistor. Now, why the resistor? Well, the current should be flowing, since it's a series circuit, the current should be the same through each device. But because we know the value of the resistance, and we know the voltage across that 7.03 volts, we can use Ohm's law to calculate the current flowing through the resistor, which ends up being 8.6 milliamps, which is very close to our measured value. So let me do a close-up real quick here of how I measure the current with the circuit. So this is originally how the resistor is wired up to the LED in the circuit. What I'm going to do is just move it over to another position here, and we have a broken circuit. So if I press the button, nothing happens because there's no path for the current to flow through. So in this case, though, I'm going to insert the meter, again, between those 2 points, and now that current is going to flow through the meter, and the light will come on, and that's when I can actually take my measurement. So the important thing is turning off the meter to the off position between every measurement. I highly recommend that. And then thinking through, what is it I'm going to measure before I make my measurement, and when I'm done, flip it back to off at the top setting. Okay, so hopefully that'll give you some insight on wiring up the LED circuit that you'll be working on this week.